Hi, my name is Dimitrios Los, and I will be presenting naively sorting evolving data is optimal and robust. This is joint work with George Giakkoupis from INRIA and Marcus Kiwi from Universidad de Chile. So I will start with some background on the evolving data model. This model was introduced by Agnostopoulos, Kumar, Mahdian, Upfel, and Banting in 2012. It says that as the sorting algorithm is executing, the input is evolving or changing. It differs from the dynamic algorithm setting, where the algorithm gets notified about which elements are evolving or changing. More concretely, every sorting step is followed by B mixing steps. And in a sorting step, the algorithm chooses a pair of indices and compares their values. Based on this output, it can decide how to update the order of the elements that it maintains. The simplest way to react to this output is to sort the pairs of values that it just compared. So, for example, if it chooses indices 4 and 6, the elements are out of order, so it sorts them. Same for elements at positions 1 and 2, and for positions at 3 and 4, it may do nothing. Now, in a mixing step, a pair of items of adjacent rank are sampled uniformly at random, and they are swapped. And importantly, the algorithm does not learn which pair was swapped. So, for example, we could pick, the environment picks values 3 and 4 and swaps them, and similarly could pick 1 and 3 and swap them, but the algorithm wouldn't learn about these values. And the aim is to maintain an ordering that is as close as possible to the true ordering. And by close, we mean in terms of maximum deviation. Maximum deviation is the maximum of the distances to its target. And in this case, it's element 2 that has this maximum distance. Another metric we care about is the total deviation, which is the sum of these distances of the elements to their targets. And it's known that this is within a factor 2 of the Kendall-Tau distance. So let us give a bit motivation for this setting. So there are several ranking problems which can be where comparisons are expensive and costly and can be modeled by this setting. And these include ranking political candidates either by conducting debates or polls, or evaluating different systems or features, and the comparison is done by A/B testing, or ranking tennis or chess players, and the comparison is done by head-to-head games, and many more. Now, sorting is also a critical subcomponent of several other algorithms. So it has been studied in other problems with evolving data, such as selection, finding the top k elements, or computing the minimum spanning tree, for example, using Kruskal's algorithm. More generally, several problems have been studied in the evolving data model, including matching, PageRank computation, community detection, several others. Now let us return to sorting, and we'll give a brief overview of previous work. So Anagostopoulos proved that a repeated version of quicksort achieves a maximum deviation of log n and a total deviation of n log n. And a more refined version of quicksort, which interleaves the execution of various instances of quicksort on small portions of the array, achieves a total deviation of n log n. And they also proved the lower bound for the total deviation of omega n, and it holds for any sorting algorithm. They conjectured that for any constant b, there exists an algorithm which matches this lower bound. Besavayel, Devani, Epstein, Goodrich, and Johnson confirmed the conjecture for b equals 1, and they showed that the repeated version of insertion sort achieves the linear total deviation in a quadratic number of steps. And this demonstrated that quadratic time algorithms are optimal for sorting with evolving data. They also showed that if you interleave the execution with quicksort, then it converges in n log n steps. However, their proof is quite tailored for the special case of b equals 1, and they left as an open problem what happens when b is greater than 1. And the same set of authors also conducted several experiments with more powerful mixing steps, and the same bounds seem to hold in these cases. One of them was the hotspot adversary, where in the mixing step an element is chosen and a direction either to the left or to the right, and the number of swaps is dictated by a geometric random variable. Finally, Mathian proposed naive sort, which samples a pair of adjacent elements and sort them if they're out of order. This is a very simple algorithm, which also has which is also local and requires no memory, so it is advantageous in various aspects. And it was conjectured that this also achieves the optimal maximum deviation and total deviation. So in our work, we prove that indeed naive sort achieves this maximum deviation of log n and a total deviation of On. And we prove this for any constant b, and it does so in quadratic number of steps, similar to insertion sort. And this resolves the conjectures and upper problems in the three aforementioned works. These bounds hold also in more generalized settings. So, for example, where the mixing steps, this displacement follows a distribution with finite moment generating function. An example is this geometric random variable with a hotspot adversary. We also relax the assumption requiring that only 1 over b plus 1 fraction of the steps are sorting, and this holds for any window of n steps. And for some of our bounds, for example, maximum deviation holds for non-constant b, and these are asymptotically tight. Further, we prove a more refined bound for the convergence time. We show that if we start with the permutation that has a maximum deviation of delta, then it converges in n times delta steps, provided delta is large enough. Further, if we interleave with quicksort, we also get the improvement in convergence time as was the case for insertion sort. Our analysis techniques are based on a novel variant of the exponential potential function, which uses dummy elements, and also on a technique for decoupling, sorting, and mixing steps. We think these may be useful for analyzing other problems in the evolving data model, as well as proving guarantees for some self-stabilizing algorithms. In the remaining part of the talk, I will give a brief outline for the analysis. This will be split into two parts. In the first part, we will prove the upper bound on the maximum deviation of log n, and then the loose upper bound on the total deviation of n log n. This will be done by first analyzing sorting steps, arguing why the normal exponential potential does not work, and showing how introducing dummy elements does work. And then we will move to analyzing mixing steps. This will be done by reducing the problem to analyzing n weakly dependent unbiased random walks. And then we will combine the two analyses and obtain the desired gap bounds. In the second part, I will give a very brief outline for the linear total deviation bound. So the exponential potential function is a very natural potential function for this problem. We basically take the distance of an element to its target, we multiply it by a smoothing parameter, and we exponentiate it and aggregate over all elements. The -1 term that we have here is to ensure that the potential is 0 if we're in the sorted configuration. Now, consider the case where we have only sorting steps, and recall that in naive sort, we sort elements in adjacent positions. What could go wrong is that there could be very few pairs that are sortable. So in this example configuration, which is obtained by splitting the array in half and swapping the two sides, there is only one sortable pair. And if we look at the elements in the first part of the array, we see that they all have the same distance to their targets. And this means that they contribute the same value to the potential function. So the problem is that the only element whose contribution to the potential function decreases in expectation is this head of the block. And this contribution must be spread equally among roughly half of the elements. So the decreased term becomes a multiplicative factor of 1 minus 1 over n squared. So 1 over n goes the probability of picking element 7, and roughly 1 over n over half the elements goes to counteract the stability of the rest of the elements. And unfortunately, these can only be used to prove that it converges in a cubic number of steps, and it is not sufficient for handling mixing steps. So how can we handle these sorted blocks? So the main idea that we use is to introduce these dummy elements, which we call gaps, and try to make these distances non-uniform. I will clarify on what non-uniform means in just a moment. So let's say we have this permutation here, and we are adding 6 gap elements. So here the targets are denoted by these subscripts, and they're evenly spaced out. And the only requirement that we have for the placement of the gaps is that if the target of an element, say for example 6, its target is here, is on the right, then the element directly to its right must not be a gap element. And the same goes if your target is to the left, the element directly to your left should not be a gap element. And the sorted state is basically having these gaps evenly spaced out. And now let's look what happens if we, for example, swap values 2 and 6. So if we swap them, then 2 would go directly to its target, and 6 would need to be swapped with all these gap elements until it reaches 1 that is non-gap, so that its element to the right is a non-gap element. Okay, so how does this fix the problem we had before? So let's place the gaps evenly on the two sides. There are other valid configurations, and they don't differ much in the main argument, so we'll concentrate on this one. So we see that the target distances increase in the first block, and the biggest one is that of the head of the block. And since the potential function is the exponential potential function, we slightly need to modify the definition so that it fits to this new array L. The point is that because it is the exponential potential and these distances increase by an additive factor of 2, the head of the block dominates the entire the contribution of the entire block. And just by using a constant fraction of its decrease, we can introduce decrease terms to each of the elements. And this means that we overall get a decrease, and we can prove this drift inequality. So here we have a multiplicative factor of 1 minus 1 over n, so no longer an n squared. And this means that it converges to a sorted sequence in just a quadratic number of steps. So now let us turn our attention to handling mixing steps. Our aim is to decouple the analysis of sorting and mixing steps. And we do this by introducing the target array. So the target array is initially equal to the identity permutation. And whenever we have a mixing step, let's say values 3 and 4 are mixed, so they're swapped in the pi array, then we also swap their target positions. So this means that their distances are, the distance of the elements to the target are the same, so the potential does not change. This, however, could introduce some problems in the sorting analysis because we need that the distances are increasing within a sorted block. So we require that if the two adjacent elements are sorted, then their targets are also sorted. And if this condition does not hold, then we do it by performing successive swaps. Each successive swap does not increase the maximum nor the total of these two distances. And so because the function, the potential function is convex, it means that it does not increase it. Recall that our main aim is to bound the total deviation for the pi array. So by using this triangle inequality, we can upper bound the first term using this sorting analysis, which involves the potential function phi. And for the second part, notice that if we fix one element in the tau array, then it has equal probability to increase by 1 or to decrease by 1, unless it's one of the boundary elements. So we can analyze this term by analyzing n weakly dependent unbiased random walks. And this can be done several ways. One of them is using a potential function with a slightly different smoothing parameter here. And actually using this potential function here is what allows us to handle these displacement distributions with a bounded MGF. So now let us combine the two analyses. So in kn steps, we have by the analysis of the random walks that the maximum deviation is in tau is at most square root k times log n. In these steps, just by the sorting steps, we have that the potential function drops by a multiplicative factor, which is roughly e to the minus omega k. And by using this rough bound on the initial value of the potential based on the initial maximum deviation, if we pick a large enough k, we can ensure that this value becomes essentially very small, which means that the potential becomes zero. So if we reset the targets, then the only term that contributes is this square root k times log n. And this means that the maximum deviation is of the order of square root k times log n. Now, if we iteratively apply this argument using this deviation as the starting deviation, then we eventually reach this maximum deviation of log n, which also implies the bound on the total deviation. I will just remark that these these bounds on the convergence time are tight, and also that these bounds hold for relaxed mixing steps. So we only assumed that each target moves by at most square root k times log n. These movements could also have been adversarial here. Okay, now we'll very briefly outline the analysis for the linear bound. So the problem is that if k is little of log n, then the maximum deviation could be omega k. So for example, if k is constant, then the maximum deviation is log n over log n. And this means that the previous upper bound does not guarantee that the potential becomes very small. So what we do instead of resetting all the targets, we reset only the ones which have a small displacement. And this means we can apply for these the previous analysis, while for the ones with the large displacement, we bound their aggregate contribution to the total deviation. And we do this via a concentration inequality on the potential function. So just to give a brief indication, so we have this potential function that covers only the elements with the small displacement. And by considering iteratively smaller and smaller intervals, we are able to show a tighter and tighter bound until we prove this linear bound on the potential function. And this in turn bounds the total deviation for elements with a small displacement. And for elements with a large displacement, we have these bounds which are bounded by a geometric sum, and they are at most On. So if we sum these two, then we obtain the desired bound. So to conclude, in this work we have shown that naive sort achieves the optimal maximum and total deviation for any constant b in sorting with evolving data. And this resolves conjectures and open problems in these three works. And the analysis also works for relaxed settings where we have mixing steps with perturbation distribution with finite moment generating function, or a relaxation on how many of the steps are sorting. And this demonstrates that naive sort is robust. There are several directions for future work. For example, handling erroneous comparisons. This has been also studied under the term biased card shuffling. Another direction is using naive sort or similar simple algorithms for other problems with evolving data, and also applying some of the analysis techniques. In particular, the decoupling of sorting and mixing steps may be of use to other problems with evolving data, while the potential function technique may be useful for other self-stabilizing algorithms. Thank you very much for listening. If you want to see more visualizations, please visit this link.